But even with 87% accurate model, how sure we are that this model is good or bad in terms of overfitting, if there are really any overfitting in the hidden model, in the model that we have seen before. So that is where we use regularization to check if there are overfitting. If there are, then we try to eliminate those overfitting through some algorithms. So as you could see, the training data is shown here with the blue points. When we try to fit in a polynomial regression or a polynomial model, then the lower order polynomial here is unable to capture the true relationship between x and y. However well you try to fit this lower order polynomial, it will never capture the true relationship. So this inability of the model to accurately capture the true relationship between the x and the y variable is what we call as bias. So this lower order polynomial therefore has a higher bias. On the other hand, you can see for the higher order polynomial, which is shown with this curvy line, kinds of hugs the training data, and it can very accurately capture the true relationship. So I'm talking all in terms of the training data now. Okay, so your model is very, very trained on the training data. That is exactly the example I tried to give you, where I ask you to read some 100 different books, and I give you questions in the exam paper, all from that 100 different books, because you have learned the book so well, you learn by heart, that any question given from the book, you will try to capture that, you will attempt it correctly. Okay, so that is what is saying here. So with the training data set, you have trained a model which is a higher order polynomial. It is very well trained on the data points. But what happens when you use the test data now? So when using the test data, you can see this lower order polynomial leads to relatively reduce you say the residual sum of the squared errors, RSS. Okay, it kind of maintain a similar error across the entire spectrum. However, for the higher order polynomial, you can see the magnitude of errors have increased. So it is not now going to work accurately on the test data. So this inability of the model to not work accurately when applied on the test data is what we call as the variance. So this higher order polynomial leads to a higher variance, but a lower bias, while the lower order polynomial leads to a higher bias, but a lower variance. So when creating a model, we make sure that we have the model having both low bias as well as a low variance. So that is again also something that so blindly doing a data science model or building a data science model does not work. Even if you have built the model, you have to be mathematically clever to remove those overfitting in the model to increase the model accuracy, right? So in a linear regression model, in a simple linear regression, you know something about cost function. So the cost function is actually minimizing the residual sum of the squared errors. So that is, so any model has a cost function component. So in case of linear regression, the cost function is how good you are in minimizing the residual sum of the squared. Now in lasso regularization, we are adding one more component to this cost function, and that is called as a lambda times the modulus of the slope. So lambda times modulus of the slope if it is a simple linear regression, but if it is a multiple linear regression, that means you have many other predictors, then we multiply lambda. So lambda is what we call as a penalty parameter or penalty component. So lambda is multiplied to the sum of the modulus of the slope. So there is not one slope. If it is a plane or a hyperplane, there are many slopes. Okay. So we are adding the same lambda. I mean, we are multiplying each slope with that parameter called lambda, which is my penalty parameter. Okay. So what is the idea behind? So typically, if you are, say, I'm giving you an example from a linear regression. This is your linear regress model, and your data points are all kind of scattered around the line. So applying this penalty component is actually doing a stepping down of the line. So the line is steepened down. So doing this, you are reducing the slope, that is the M. Okay. So when it is a multiple predictor system, when you are multiplying lambda to the sum of the modulus of the slope, it all means that you are kind of reducing the slopes of the hyperplane or the plane equally. So in doing that, you are trying to, those predictors which had a very, very high slope will have their slopes shrink a bit. And those predictors which were actually irrelevant, had no interaction with the response variable, they had a slope very close to zero, but their presence was kind of creating problem. So their slopes will be kind of reduced to zero. So this way, I'm eliminating those features which are actually irrelevant in my entire data set by adding this lambda component. Is that clear? So to our logistic regression model, where we have this log of p by 1 minus p as the response variable, we are adding to its cost function this lambda times the sum of the modulus of the slopes. Okay. Now, using a cross validation, that uses a generalized linear model under regularized setup. We got this plot of something called as a binomial deviance versus log lambda. So I'm again not covering what is binomial deviance. So we are trying to look at capture that value of lambda for which my binomial deviance is minimum. Okay, and we are plugging that lambda value to our model equation. And when this model equation is tested over the test data, we are again getting a kind of histogram for the predicted success probability. Okay, so what we can see, this probability distribution or the histogram, I would say, is very similar to what you have obtained in the past in the logistic regression model. And further to that, I also got an AUC value, which is 0.9, and accuracy, which is 87%. So together, all these things appears to be very similar what you obtained in your logistic regression model. Therefore, we can conclude that the existing logistic regression model does not have significant overfitting and therefore can be used with confidence. Is that clear? Okay. So just answer me over the chat box. I'll possibly take another 15 minutes to finish this session and then keep some time for discussion. I'll then unmute you all. Just let me understand the response. If it is, please reply with chat until now. If okay, thank you. Any other response? I see only from one participant. I just do okay, fine. Okay, so other thing that you can also see that if you have no overfitting in your model, then typically lambda value is close to 0, and that is another way of checking. If my lambda is close to 0, there is you are confident there is no overfitting in the model, so you can go ahead with this existing model. Now,